For decades, scientists have been chasing this almost mythical dream. What if we could harness the power of a star, right here on Earth? Well, today we're diving into a massive breakthrough that takes this idea of a man-made sun and brings it one giant leap closer to being our reality.
I mean, just think about that question for a second. What would it actually mean for all of us if we could build our own star? It sounds like something straight out of science fiction, right? But it is the very real, very serious goal behind the entire quest for nuclear fusion. So, what's the science here? At its heart is something called nuclear fusion. It's the exact same process that powers our sun. The concept is actually pretty simple. You take atomic nuclei, you smash them together with incredible heat and pressure, and they fuse into a new one, releasing just a staggering amount of clean energy in the process. Okay, so let's start with this idea. The sun on Earth. Because that fundamental process, nuclear fusion, it's the absolute key to this whole thing. It's why scientists are so incredibly determined to recreate it. And the prize if they succeed? Oh, it's nothing less than the ultimate energy source. We're talking about power that's totally clean, no greenhouse gases. It's sustainable, using fuel that's abundant in plain old seawater. And it's virtually limitless. It is, without a doubt, the holy grail of energy. So, that brings us to fusion's toughest problem. If the goal is so amazing, why don't we have fusion power plants lighting up our cities already? Well, it's because trying to build a star inside a box turns out to be one of the toughest physics problems humanity has ever tackled.
See, to get fusion to work, you need to contain something called plasma that is literally hotter than the core of the sun. Obviously, no physical material can touch that. So scientists came up with this incredible device called a tokamak. You can think of it as a magnetic bottle. A giant, donut-shaped machine that uses unbelievably powerful magnetic fields to hold and shape that super hot fuel.
And this is where fusion research basically hit a brick wall. For decades, there's been this hard and fast rule known as the disruptive density limit. To put it simply, if you try to pack too much fuel, if you make the plasma too dense, it becomes violently unstable. This not only kills the fusion reaction instantly, but can seriously damage the incredibly expensive, multi-billion-dollar machine. It's been a fundamental barrier to making any real progress. This created a really frustrating paradox. You see, to get efficient energy out, you need high plasma density and a totally stable reaction. But that old limit meant that any time you push for that high density you needed, you'd cause a massive instability, leading to terrible energy output. It was a classic catch-22. So let's talk about a new theoretical clue. Because, science rarely stays stuck for long. A new idea started to emerge, not from an experiment, but from a totally new way of thinking about the problem. That clue came from a new theory with a bit of a mouthful of a name, the plasma wall self-organization theory. But what it did was offer a completely fresh perspective, suggesting that maybe, just maybe, this disruptive density limit wasn't the absolute law of physics everyone thought it was. And here was the core idea. The theory predicted that if you could get the conditions just right, a super delicate, specific balance between the insanely hot plasma and the reactor's metallic walls, you could create something called a density-free regime, a whole new way of operating where that old limit just vanishes. And that, my friends, brings us to the really exciting part, the East breakthrough. A team of researchers decided it was time to put this new theory to the test in the real world. Okay, so this all went down at a facility called EAST. That's the Experimental Advanced Superconducting Tokamak over in China. The work was led by a team including researchers Zhu Ping and Yan Ning, and their absolutely groundbreaking results were published in the journal Science Advances. So how'd they do it? Well, their new method had two really clever steps. First, they got super precise control over the fuel gas pressure right at the very start. Then, during that initial startup, they zapped it with a special kind of microwave heating. You can think of it like a highly focused, extremely powerful microwave oven that let them manage the plasma's temperature right from the get-go. The real genius of this approach was how it gave them total control. By combining these two steps, they could perfectly manage those delicate interactions between the plasma and the reactor wall right from the start of the experiment, exactly what the new theory said they needed to do. And the result? It worked. That long-standing, stubborn, decades-old barrier, the disruptive density limit, was broken. And the outcomes were just incredible. They pushed the plasma density way beyond the old limit, and they did it without triggering any of those dangerous instabilities. But get this, on top of that, their method also cut down on impurities and heat losses from the plasma, which happened to be two other massive hurdles for fusion. It was a win-win-win. Now, this brings us to what's next.
a practical path forward. Because this amazing result wasn't just some clever lab trick. It has carved out a real, tangible path forward for the entire field of fusion energy.
And don't just take my word for it. As the lead researcher Zhu Ping explained, this isn't just a one-off result. He said their findings point to a method that is both practical and scalable. And that word, scalable, is so important. It means this technique could actually be used on the next generation of even bigger, more powerful fusion reactors that are being built right now.
And you know the team isn't stopping here. Another one of the researchers, Yan Ning, says their very next step is to apply this exact same method during the machine's most demanding, high-power operations. They want to push the reactor to its absolute limits and see just how far this new density-free way of working can go.
By completely shattering a barrier that stood in the way for decades, this work doesn't just advance the science, it could very well accelerate the entire timeline for fusion energy. Which leaves us with this one tantalizing final thought. How much closer are we, right now, to a future powered by our very own star?